Join us as we drift through a mystery written in the stars. Somewhere beyond the orbit of Jupiter, an interstellar visitor named 3I Atlas is changing direction, and no one can explain why. It isn't loud. It isn't spectacular. It's quiet, steady, impossible. For months, telescopes around the world have watched this small, frozen traveler glide through the darkness, calm, silent, and defying the very laws that brought it here. Gravity should be enough to predict its motion. Yet, something unseen is touching it, bending its path with the gentlest of hands. Tonight, we'll follow that story. The data, the doubt, the wonder. We'll listen to the scientists tracing a force they cannot name, and the silence between the stars that hides its source. So, take a breath, let the noise fade, and join us as we look into the unknown. A gentle push from nowhere. When the news of 3I Atlas's trajectory shift reached the Jet Propulsion Laboratory in Pasadena, it arrived as a quiet anomaly buried in a routine report. There was no urgency, no alarm, just a line in an email that read, "Observed, offset, increasing. Potential non-gravitational acceleration persists." In a field that deals in precision, those few words were enough to stop conversations mid-sentence. The object, long presumed predictable, had changed its behavior again. At first, no one wanted to say the word unexplained. Astronomy is a discipline that prefers errors to mysteries. Errors can be fixed. So the first step was always the same. Check the instruments. Observers recalibrated star catalogs, verified timing sequences, reprocessed the raw frames. They looked for tracking glitches, background contamination, cosmic rays that might have nudged pixel brightness just enough to fool the software. Nothing surfaced. The deviation remained consistent across telescopes, across continents, across time. By mid-June, the displacement had stabilized at nearly 2,500 kilometers from the predicted position, corresponding to a transverse acceleration of about 4 times 10 to the power of -7 meters per second squared. It was minuscule, the kind of number that should vanish under rounding errors, but in celestial mechanics, such a force mattered. Over millions of kilometers, it could alter a comet's fate completely. At the University of Maryland, Tony Farnham and his team began running dynamic models using the Marsden non-gravitational parameters, testing every plausible configuration of jets and rotation. The problem wasn't that the acceleration existed. It was that it pointed in the wrong direction. If this were normal outgassing, he explained during a briefing, the vector should align roughly with the Sun-comet line, but it's offset by nearly 40 degrees. That's not how sublimation behaves. Other possibilities surfaced. One theory proposed that 3I Atlas might have shed a fragment, a chunk of nucleus large enough to change its momentum, but too small and dark to detect. Yet even that required fine-tuning. The shift had continued steadily for weeks, not suddenly as a mass loss event would suggest. Another idea suggested an uneven distribution of trapped gases, releasing in sequence as the comet rotated. But by this distance, more than 800 million kilometers from the Sun, most volatiles should have frozen solid again. The physics didn't add up. Meanwhile, the European Southern Observatory commissioned a rapid series of follow-up observations. For 5 nights in late June, the Very Large Telescope pointed toward the faint coordinates where 331 Atlas was expected to be. The object was barely visible, its magnitude hovering near 21. The images confirmed the offset and, crucially, showed no visible jets. The coma, if it still existed, had collapsed into a point source, a frozen relic coasting through darkness. "It's dead," one researcher whispered when the images were displayed. "Then why is it moving like it's alive?" Came the quiet reply. That tension between the visible and the measurable defined the weeks that followed. Teams at NASA, ESA, and the International Astronomical Union cross-checked their ephemerides. Every model was updated with the new data, and every model failed to converge. By early July, the predicted orbit and the observed one diverged by more than 1,000 kilometers per week. For a comet with no detectable activity, the result was confounding. Some scientists returned to the oldest explanation in their toolkit: solar radiation pressure. The force of sunlight, though gentle, can nudge small objects through cumulative momentum transfer. It had once been invoked to explain the acceleration of Oumuamua, but even that had limits. For radiation pressure to produce the observed deviation, 3I, Atlas, would need a surface area to mass ratio far higher than expected, something thin, hollow, or unusually light. Yet the Webb data from months earlier suggested the opposite: a dense, cohesive nucleus. There were whispers, of course there always are. When data refuses simplicity, imagination rushes to fill the void. Blogs speculated about alien probes, light sails, or magnetic interactions beyond current models. But within the professional community, the tone remained disciplined. "It's not extraterrestrial," said astronomer Karen Meach during a webcast. "It's just unfamiliar. Nature is still better at surprises than we are at predictions." Through July, the object drifted farther from sight. Only the largest telescopes could still detect it, yet the acceleration persisted, measurable in the slow widening of the error margins. By August, the deviation vector had rotated slightly, as though responding to something variable. That shift drew the attention of plasma physicists, who wondered whether the comet might have encountered a region of differing solar wind density, a boundary where charged particles flow unevenly. The idea was plausible but difficult to prove. At that distance, direct measurements of solar wind are rare. It could be a magnetic gradient, suggested ESA scientist Olivier Hainaut. But without a probe out there, we can't test it. In private correspondence, some scientists began referring to the anomaly simply as the drift. The term carried no assumptions, not cause, not consequence, only observation. The drift was real. The drift was measured. The drift was unexplained. By September 2026, the comet had receded beyond 6 AU from the Sun, its faint glow lost amid background noise. The last images came from the Subaru telescope in Hawaii, confirming what many already suspected. The acceleration had diminished, but not ceased. 3I Atlas was now moving slightly faster, and at a slightly different inclination than when first detected. Its outbound course, projected forward, would miss its expected galactic trajectory by a fraction of a degree, a small change, but one that, over millions of years, would send it toward an entirely different region of the Milky Way. For those who had followed it since discovery, the deviation became less a problem to solve and more a reminder. The universe does not promise consistency. It gives patterns, then exceptions, equations, then silence. Somewhere beyond Jupiter's orbit, a dark, frozen body continued its journey, bearing a force we could measure but not yet name. And on Earth, the watchers wrote their reports, archived their data, and waited for the next visitor that might do the same. When gravity wasn't enough, in the weeks after 3 vanished beyond the range of most telescopes, the conversation did not fade, it deepened. In data centers from Pasadena to Geneva, astronomers stared at residual plots that refused to flatten, their screens glowing with evidence of something that gravity alone could not explain. The numbers were consistent, clean, and maddening. The object had accelerated, slightly but persistently, in defiance of every known model. Gravity had done its part. Physics had not finished speaking. The first coordinated attempt to solve the puzzle began at the Jet Propulsion Laboratory. A symposium titled Non-Gravitational Dynamics in Hyperbolic Objects convened in early October 2026. The participants were cautious by nature: orbital dynamicists, plasma theorists, and comet physicists who preferred millimeters and seconds to headlines. Yet, even among such precision, there was tension. On the second morning, a plot projected across the room showed the divergence curve a thin blue line bending away from the predicted path. Someone murmured, "It's the same shape as Oumuamua's." The room went quiet. They began by exhausting the obvious. Outgassing was revisited first. Could unseen jets of sublimating gas produce the measured force? Using models built from 2I divided by Borisov's activity, the team calculated the required gas flux. It was too high. To sustain that acceleration, You'd need a vent the size of a football field, said one researcher. And yet there's no coma. Webb's infrared spectra had detected no additional carbon monoxide, no trace of volatile release since February. Whatever was pushing the comet, it wasn't escaping gas. Solar radiation pressure came next. For a moment, it seemed promising. A reflective surface, however faint, can generate thrust under constant sunlight. But the effect falls off with distance. And 3I Atlas was already far beyond the inner solar system when the acceleration began. Moreover, the direction of the deviation wasn't radial from the sun, it was skewed, as though angled by an unseen vector. You can't push sideways with photons, quipped a physicist from MIT. Laughter followed, but it carried fatigue. Magnetic fields offered another avenue. Plasma physicists examined data from the Parker Solar Probe and the Solar Orbiter, both of which had recently measured subtle irregularities in solar wind density near the ecliptic. Could a pocket of charged particles, drifting outward, have altered the motion of the comet's ionized tail? Perhaps. The hypothesis fit some of the data, the timing, the gradual onset, but failed in one critical aspect. The direction again. The solar wind flows outward. The force on the comet was lateral. We're chasing a ghost, one scientist admitted, closing his laptop. By November, simulations filled the servers. Each run produced the same truth. The numbers fit nothing cleanly. The deviation was real, coherent, and small enough to evade easy categorization. To the untrained eye, it looked like noise. To those who measured orbits for a living, it looked like intent, not in a sentient sense, but in a mathematical one. Something was acting consistently across time, imparting motion without visible cause. The discussions shifted from the physical to the systemic. Had they misunderstood something about interstellar comets themselves? Perhaps these objects carried internal dynamics we hadn't yet seen in solar system bodies. If 3I Atlas had a layered structure, dense crust, porous interior, its thermal conductivity might cause asymmetrical expansion as it cooled. Microscopic fracturing could produce gas flow too faint to detect yet strong enough to alter motion. It was plausible, but difficult to model. We might be seeing a new class of thermodynamic behavior, said planetary scientist Olivier Hainaut. These are materials forged under alien suns. We shouldn't expect them to act familiar. At the European Space Agency's Mission Design Center, engineers took a different view. To them, the anomaly was less a mystery and more a calibration opportunity. The unmodeled force, once quantified, could help refine the precision of future intercept missions. If we can't explain it, we can at least prepare for it, said Colin Snodgrass, referencing the upcoming Comet Interceptor. His team began incorporating an unknown force tolerance parameter into navigation algorithms, a pragmatic acknowledgement that the universe occasionally bends its own rules. Outside scientific circles, the story attracted quiet fascination. Headlines used phrases like, "the comet that changed its mind," and "the drift of the unknown." But the scientists themselves resisted the pull of drama. They spoke of statistics, uncertainties, and the slow grind of analysis. Behind the careful phrasing, though, was wonder. To find something that obeys gravity perfectly and then doesn't, that is not threat, but revelation. "Every deviation is a teacher," said Karen Meach in a radio interview. "It shows us where our map of the universe needs another line drawn." Through the winter, the comet remained unseen, but the models continued. The last usable data points came from archival images taken by the Subaru telescope, reprocessed for faint signals. Even there, the drift was visible as soft bend, an echo of motion where only straightness was expected. The discovery was rechecked, confirmed, and added to the growing consensus. 3I Atlas had experienced a real, measurable, sustained acceleration that could not be attributed entirely to known forces. For some, that was enough. The phenomenon required no exotic explanations. In a galaxy of 100 billion stars, diversity of matter meant diversity of behavior. Interstellar comets might simply be messier, more complex, more alive with chemistry than the pristine archetypes we knew. Others, however, found themselves uneasy. If this was not outgassing, not radiation, not magnetism, what else was left? Theories grew abstract. Differential mass loss, interstellar dust impacts, or even faint gravitational influences from passing bodies unseen. None satisfied everyone. By year's end, the anomaly settled into data tables, stripped of mystery but not meaning. Papers were written, simulations archived, conferences scheduled. And yet, among those who had watched the numbers first bend and then refused to straighten, a quiet understanding remained. The universe had offered them a small defiance, a reminder that its laws were written in pencil, not ink. Somewhere beyond Saturn's orbit, 3I Atlas continued its silent departure, not defiant, not miraculous, merely different. Gravity had been its guide for billions of years. For a moment, something else had touched it, a breath, a force, a whisper, and then released it again, the curve in the dark. Long after 3I Atlas had vanished from every telescope, the data remained millions of numbers quietly archived in digital vaults around the world. Positions, magnitudes, spectra, timestamps, the faint record of a traveler no longer visible. Years passed, but the curve of its path still haunted orbital analysts, a faint bend through space that refused to straighten. It became not just an orbit but a question frozen in mathematics, a reminder that something out there had moved differently and left behind a trace too subtle to forget. By 2028, the comet's direct detection had long ended, yet its residual acceleration continued to ripple through simulations. The Jet Propulsion Laboratory's Solar System Dynamics Group kept it on their active watch list, not because they expected it to return, but because its data wouldn't converge. Each time the equations were rerun with new gravitational models, the same distortion appeared, a small, consistent curvature that shifted its galactic exit vector by half a degree. The difference was minuscule, like a coin's edge, compared to the width of a continent, but in orbital terms, it was enormous. In Geneva, the European Space Agency's data archive received a request from a young researcher named Amara Lind. She wanted every observation ever made of 3I Atlas, raw and unfiltered. Her goal was simple: to see if modern machine learning algorithms could find a pattern that the human eye had missed. Over months, she trained her model on the comet's positional data, feeding it thousands of frames from Atlas, Pan-STARRS, and the Very Large Telescope. The program learned to predict where the comet should have been, then compared those predictions to where it actually was. The residuals glowed faintly on the screen like threads of static, each one pointing the same direction. "It's beautiful," she wrote in her notebook. "It's consistent, and it shouldn't be there." The anomaly was small, smooth, and perfectly timed. It rose gradually, plateaued, and then diminished an elegant arc of deviation. The pattern suggested not a sudden impulse, but a gentle, continuous interaction, lasting months. When Lind shared her findings with the ESA team, they stared in silence. "It's almost too clean," said one analyst. "Natural processes are messier." The phrase hung in the air, heavier than intended. The reanalysis spread. NASA revisited its telemetry archives, checking whether any solar wind irregularities had passed through the region during that time. The Parker Solar Probe's data showed mild fluctuations in magnetic density, but nothing coherent enough to explain the curve. The plasma models, when plotted, looked chaotic storms and eddies, not steady flows. "If the comet wrote a current," said physicist Mark Stevens, "that current left no signature." Attention turned to interstellar dust. Beyond the orbit of Saturn, the solar system merges gradually into the heliopause, a region where the sun's magnetic influence fades and galactic particles drift freely. Perhaps 3I Atlas had passed through a pocket of denser dust, creating drag or electrostatic charge that altered its course. Simulations run at the Max Planck Institute showed that such an encounter could produce deflection on the same order of magnitude, but the duration didn't fit. The observed curvature lasted longer, too smooth to be a single event. "It's not a bump," Stevens wrote. "It's a tide." Meanwhile, in an office overlooking the Pacific, Karen Meach reread her notes from the earliest nights of observation. She had been there when the first images came in, when the object was just a faint speck among millions. Now, years later, it had become a symbol not of discovery, but of humility. "We map the universe by light," she said to a visiting journalist. "But sometimes the dark parts draw the map for us." The phrase would later appear as the title of her paper, Mapping by Darkness: The Non-Gravitational Legacy of 3I Atlas. Her argument was quiet but radical. She proposed that interstellar objects like Atlas might act as tracers of unseen galactic structures, faint gravitational gradients, or subtle variations in the Milky Way's local potential. Perhaps we're not watching a comet move oddly, she wrote. Perhaps we're watching the fabric of space curve beneath it. The idea wasn't mystical, it was practical. Every mass, every cloud, every unseen cluster of cold dust exerts influence. We just rarely have test particles crossing those regions. 3I Atlas might have been the first. The hypothesis sparked cautious excitement. For decades, astrophysicists had measured the galaxy's structure indirectly, through starlight and radio emissions. But here was a possibility of using motion, the trajectory of small, passing bodies, as probes of the gravitational field itself. It was like watching leaves drift on an invisible river to map the current's shape. Maybe this isn't a comet's secret, said Olivier Hainaut. Maybe it's the galaxy's. In 2029, Lynn's machine learning analysis was published, co-authored with Meach and Farnham. The paper concluded that while 3I Atlas's deviation could not be explained by internal forces alone, it might represent the first measurable instance of an interstellar object responding to local galactic curvature, the gentle gradient where the solar system's gravitational influence meets that of the Milky Way's mass distribution. The result was tentative, not proof, but it offered a new language: microgravitational drift, a phrase for a force too faint to name, yet too persistent to ignore. Even after publication, the mystery stayed personal. Lind kept the comet's curve as her computer background, a thin white line against black, bending almost imperceptibly. It reminds me, she said, that even straight paths aren't truly straight. And somewhere far beyond Neptune, the object itself continued along that unseen bend. It no longer glowed, no longer reflected enough light to measure. Yet in databases and graphs, its presence endured a record of motion that whispered of larger shapes, invisible landscapes etched into the gravity around us. The curve in the dark was not an answer. It was a reminder that the universe speaks softly, that the truth sometimes hides between decimals, and that every departure, however small, might just be the shape of something vast turning unseen beyond our sight. Unseen currents. By the time the last confirmed coordinates of 3I Atlas faded into uncertainty, the world's telescopes had turned their gaze elsewhere. New comets, new surveys, new data streams filled the sky. Yet beneath those shifting priorities, one mystery persisted, a soft echo in the numbers. The unexplained curve. The anomaly was small enough to ignore, but no one truly did. It lingered, patient and unresolved, like a low note under the music of new discoveries. In early 2030, the European Space Agency's Gaia mission released its third full astrometric catalog, an immense dataset mapping the positions and motions of nearly 2 billion stars. Hidden within those star tracks was something unexpected: faint statistical irregularities in the region where 3I Atlas had crossed the ecliptic. The deviations were microscopic, no larger than observational noise, but a few analysts noticed patterns that matched the comet's deflection vector. It was as if the space itself, not the comet, had shifted. The findings reached the attention of astrophysicist Dr. Amara Lind, now working with ESA's Advanced Dynamics Group. She had spent years studying that same bend in 3I divided by Atlas's orbit, the curve that shouldn't have existed. When she saw the Gaia anomalies, she felt a strange mix of recognition and disbelief. "They're pointing in the same direction," she told her colleagues. "It's subtle, but it's there. The current runs through everything." The phrase stuck. The current. Scientists began using it informally to describe the hypothetical region of faint gravitational distortion, a place where forces blended, twisted, or intersected between stellar domains. Some treated the idea as metaphor, others as measurable hypothesis. Either way, the term had power. If space truly contained invisible currents, they might explain why small interstellar objects like Atlas occasionally drifted off course. They would be the hidden rivers of the Milky Way, intangible, yet real. In mid-2031, ESA approved a modest mission to test the theory. It was called Vigil, a cube probe no larger than a washing machine, designed to piggyback on a larger Jupiter transfer vehicle. Its task was simple: to measure local gravitational gradients and particle densities as it moved outward through the heliosphere. It couldn't catch 3I divided by Atlas. The comet was already billions of kilometers away, but it could follow its trail. Instruments aboard Vigil would scan for minute accelerations, electromagnetic fluctuations, or shifts in dust density that might reveal the faint current theorized from Atlas's data. Vigil launched quietly in late 2032. No live streams, no headlines, just a small signal blinking in deep space. Its sensors, though modest, were sensitive enough to detect changes in acceleration as small as 10 to the power of -8 m divided by s squared. The spacecraft drifted beyond the orbit of Jupiter by 2034, its trajectory calculated to intersect the projected path, where 3I divided by Atlas had once passed. Scientists watched its telemetry like whispers on a graph. For months, nothing happened. The numbers were stable, boring, predictable. Then, one afternoon, the signal showed a blip, an anomalous drift of 0.0004 meters per square second over 40 minutes. It wasn't much. It could have been cosmic noise. Yet the direction matched the same orientation as the comet's unexplained deviation 8 years earlier. "It's small," Lynn said during a debrief, "but it's the same fingerprint." The results were logged, rechecked, debated. Solar radiation fluctuations? No, the timing didn't fit. Instrumental error? Unlikely. The shift appeared across multiple redundant systems. The anomaly repeated twice more, faint but consistent, over the following months. Each time the vector pointed roughly along the galactic plane, not toward the Sunday. It was as if the probe had brushed against an invisible tide. NASA's Jet Propulsion Laboratory took notice. Using the Vigil data, they ran reverse simulations, reconstructing the spatial structure that could produce such forces. The resulting models looked nothing like planetary gravity or solar wind patterns. They resembled sheets, vast, folded gradients extending across hundreds of astronomical units, their strength vanishingly small but coherent. "If they're real," one engineer remarked, "we've been flying through invisible weather our whole lives." The implications rippled quietly across the scientific community. Papers appeared in astronomy and astrophysics and nature physics, each cautious but captivated. The term microtides entered the lexicon. Minute gravitational variations caused by diffuse interstellar matter. Perhaps dark matter filaments. Perhaps something simpler, like gradients of unseen dust. Nothing conclusive, only possibilities. But the language had shifted. The anomaly of 3I Atlas was no longer an isolated event. It had become evidence of a wider structure, an unseen topography beneath the stars. Meanwhile, Vigil continued outward, its systems aging gracefully in the cold. Its transmissions grew faint, its course stable. In December 2035, as it passed 15 astronomical units from the Sun, its final data packet arrived weak, distorted, but complete. Inside the telemetry logs was one last acceleration spike, measured at nearly the same amplitude as before, the same signature, the same direction. Then, silence. The signal ended, and with it, the mission. The data were enough to confirm one simple truth. Whatever had touched 3I Atlas was not unique. The same faint pressure existed still, subtle and wide as a cosmic breeze. "We can't see it," Lynn said in her final briefing, "but we can feel its effect. The universe has its own tides." That phrase, "the universe has its own tides," found its way into articles, documentaries, and classrooms. It describes something profound but invisible, the idea that motion, even in perfect vacuum, is never entirely free. Every star, every grain of dust, every drifting comet moves through a vast, slow current, the gravitational echo of creation itself. Somewhere far beyond the reach of Vigil, beyond the Sun's fading influence, 3I Atlas continued along that unseen flow. Its path was no longer a straight line into darkness, but part of something larger, a subtle arc drawn by the quiet forces that weave the galaxy together. And on Earth, beneath bright city skies, the data glowed on monitors, faint traces of a motion still unfolding. Scientists called it a discovery. The poets called it something else. Proof that even in silence, the universe moves us all. The drift beyond prediction. In the years after the Vigil probe went silent, the mystery of 3I Atlas evolved from a question into a pursuit. The data it left behind, the subtle arc, the whispered acceleration, the microtides that shaped its path, became the foundation for a new era of interstellar exploration. What began as a single anomaly had become a map, not of a destination, but of movement itself. The universe, it seemed, had currents. Humanity was finally learning how to follow them. By 2036, the term interstellar dynamics had entered official vocabulary. The European Space Agency, NASA, and JAXA jointly founded the Interstellar Trajectory Initiative, a research program designed to develop spacecraft capable of both observing and reacting to unpredictable motion. The lesson from Atlas was clear: precision alone wasn't enough. You had to build flexibility into the design to expect deviation as part of the natural order. At JPL, engineers studied the visual telemetry line by line. The faint accelerations it recorded, though barely perceptible, contained rhythm pulses that hinted at periodic interactions with invisible density gradients in space. "It's like turbulence, but gravitational," said systems engineer Maya Ortiz. "We're learning to read the weather between stars." As engineer Maya Ortiz. "We're learning to read the weather between stars." From those lessons emerged Project Lumen, the first mission concept designed not to chase a known target, but to wait for one. Stationed beyond Mars, at the Sun-Earth L2 point, Lumen would deploy a swarm of 12 lightweight probes, each capable of autonomous course correction using micro-ion propulsion and AI-guided navigation. Their sensors would monitor particle flux, radiation, and gravitational variation. The goal: when the next interstellar visitor was detected, one or more of the Lumen craft would slingshot outward to intercept it, adapting to its drift in real time, no matter how unpredictable. It was, in every sense, a child of 3I Atlas. The comet that had defied gravity had also rewritten the rules of pursuit. At first, the idea sounded impossible. To catch an object moving faster than any human spacecraft, launched with almost no warning, required coordination across nations and technologies. But the data didn't lie. If microtides and unseen currents could shape interstellar trajectories, then prediction models had to change. The old equations, Newtonian, clean, deterministic, no longer sufficed. Instead, mission planners adopted probabilistic navigation, a concept closer to fluid dynamics than classical mechanics. A spacecraft would no longer follow a single predicted path, but swim through a probability field, guided by feedback and correction. It was navigation by uncertainty, the art of trusting the drift. In 2038, as Lumen's components were being tested, a new discovery reignited the global fascination. The Atlas survey, its sensors upgraded for faster scanning, detected another faint, hyperbolic object entering the solar system from the direction of Cygnus. The designation came quickly: 4I divided by tau, named for its angular position near the star Tau Cygni. Within hours, headlines declared it the successor to Atlas. Its brightness was faint, its trajectory erratic, its approach fast. But what electrified scientists was one number: its initial velocity. It matched, almost perfectly, the outbound vector of 3I Atlas, as though the two had once shared a distant origin. The timing was uncanny. The world's observatories mobilized in hours. Lumen's launch schedule was advanced by months. Within a week, 3 of its probes were deployed, their micro-thrusters flaring to life, adjusting to intercept the path of 4I divided by tau. The world held its breath, watching as the swarm accelerated toward deep space. At the control center in Darmstadt, Amara Lind stood beside the mission's director as data streamed in faint telemetry signals from the tiny machines already thousands of kilometers away. The first probe, Lumen A, confirmed contact with a trail of interstellar dust. The second, Lumen D, registered a weak acceleration almost identical to what 3I Atlas had exhibited a decade earlier. "It's happening again," Lynn said softly. "The same push." For scientists who had spent years wrestling with invisible math, it was vindication. The universe's subtle forces weren't coincidence, they were structure. The data showed consistent deviations aligned with the galactic plane, proving that space was not an empty void, but a fabric shaped by density, dust, and time. The interstellar medium wasn't passive. It flowed. The Vigil probe had brushed its edge, had traced its pattern. Now, humanity was entering it willingly. As Lumen's probes closed in on 4I divided by tau, they began transmitting unprecedented detailed particle counts, field variations, microgravitational vectors. The data revealed fluctuations so fine that even light seemed to bend microscopically. "It's like the ocean," said mission scientist Jessica Agarwal. "We're floating on ripples too large for us to feel directly." For the first time, humanity had built a machine to sail those ripples. Each probe moved, as if alive, adjusting, correcting, adapting to invisible tides. Their paths, plotted on screens back on Earth, not defiance, but flow. The discovery reshaped more than science. It altered philosophy. The idea that movement was never absolute, that every journey is curved by the unseen, echoed beyond astrophysics. Writers, artists, and thinkers began invoking the drift as metaphor, the subtle push of unseen forces shaping existence. The story of a comet had become a story of everything. By 2040, Luhmann's mission had gathered enough data to map the first interstellar flow field model, a simulation of gravitational and density gradients across the solar frontier. It revealed the solar system not as an isolated bubble, but as part of a vast, slow spiral of matter, winding through the galaxy, a cosmic current connecting countless worlds. And in that current, 3I Atlas was just one leaf, briefly illuminated, carried by the same invisible river that now bore humanity's machines. No one ever found out precisely why the comet changed direction. But in trying to answer that question, humankind discovered something greater, that motion is never singular, and space itself is alive with quiet intent. Somewhere far beyond the reach of Luhmann's sensors, perhaps near the interstellar boundary, 3I divided by Atlas still drifted, steady and silent, not lost, not gone, simply moving with the tide, the first messenger of a current no one had known was there. Noise, or message. The first time the pattern appeared, no one noticed. It was buried deep inside a telemetry packet from Luhmann D, timestamped the 3rd of September 2040, routine background data, nothing unusual. The probe was still outbound, skimming the outer edge of the solar system, its sensors tuned to detect gravitational drift and particle density. In between those clean lines of numbers lay a faint repetition, 6 pulses of irregular amplitude, repeating every 17 minutes. At first, the data processors at JPL flagged it as thermal cycling noise, a common artifact from temperature changes. The file was logged, archived, forgotten. 3 months later, a graduate student named Haijin Park reopened that same packet for a data cleaning audit. Her task was mechanical remove instrument noise before public release. But when she applied a filter to the signal, she noticed the pulses didn't fade. In fact, they strengthened. The rhythm wasn't random. It followed a consistent envelope curve energy, rising, falling, rising again, with precision too neat to be thermal noise. Out of curiosity, she ran a Fourier transform. The result formed a single, sharp frequency peak. One tone, stable, persistent. Park sent an internal note to her supervisor. The reply came hours later, cautious but curious. "Check the next week's logs, see if it repeats." It did, and not just in Luhmann D's telemetry. 2 other probes, Luhmann B and Luhmann F, had recorded the same faint pulse at slightly staggered intervals, each delayed by the distance separating them in space. The signal arrived sequentially, as though passing through them one after another, moving outward along the same vector, once followed by 3I Atlas. By January 2041, the anomaly had become a matter of quiet urgency within the Interstellar Trajectory Initiative. A special task group formed, composed of radio engineers, astrophysicists, and signal analysts. Their first step was to eliminate every conventional source. Cosmic rays? No, the pattern was too stable. Solar wind modulation? Unlikely, its frequency was too regular, and the probes were in different magnetic zones. Internal clock interference? The phase offset between probes disproved that immediately. "It's external," said systems engineer Maya Ortiz, pointing to the synchronized drift. "Something's moving through them." The discovery leaked before the team was ready. An astronomy blogger in Toronto noticed an irregular timestamp update in the Luhmann telemetry archive metadata that hinted at signal reprocessing. Within days, speculation flooded social media. Alien message confirmed? The official response from ESA was brief. No evidence of artificial origin. The signal is under review. Behind closed doors, however, review turned to fascination. The pattern had characteristics of structure, but not communication. It didn't modulate, didn't encode binary, didn't carry phase shifts. It was pure rhythm, the kind nature produces only under conditions of resonance. Its frequency corresponded to a wavelength of 1.75 million kilometers, enormous, far too long for any electromagnetic emission within normal plasma dynamics. And yet, it was real. "It's not sound," Lynn said in a meeting, her voice calm but steady. "It's structure. We're hearing the motion of the medium itself." Her hypothesis was daring. The pulse wasn't a signal sent, it was a byproduct of the microtides themselves, oscillations in the interstellar current that Lumen had entered. Like a standing wave on a vast, invisible ocean, repeating as it propagated outward. If true, it meant space was not static even at galactic scales. It vibrated faintly, rhythmically shaped by gravity, dust, and time. Deviation years earlier might have been the first physical trace of this same resonance. The next step was to test it. Engineers instructed the surviving Lumen probes to rotate and reorient their high-gain antennas, capturing the pulse at multiple angles. The data confirmed the signal was directional, not omnipresent, but aligned precisely with the galactic plane. Moreover, its strength increased slightly whenever the probes crossed, predicted density ridges in the interstellar model. The resonance was not random background noise, it was following structure. When plotted on a graph, the pulses formed a pattern of breathtaking simplicity. A sine wave nested within a broader modulation, the cosmic equivalent of a heartbeat. 6 beats, pause, repeat. Always 6. Always steady. The data team began calling it the hum. Weeks passed, then months. The hum persisted. It drifted subtly in amplitude, but its core frequency never wavered. Scientists compared it against gravitational wave background data from LIGO and the European Pulsar Timing Array. No correlation. It was something new, something too slow and wide to fit into any known category of wave. A paper was drafted, then withdrawn. The authors couldn't agree whether the hum qualified as discovery or anomaly. The debate grew philosophical. "If it's natural, we're hearing the universe breathe," said Ortiz. "If it's not, we're not ready to understand it." Lind proposed one final test: to aim Earth's most sensitive radio telescope, the Square Kilometre Array in South Africa, at the coordinates along which the hum originated. For 10 consecutive nights, the array listened. It detected nothing. Silence. Whatever resonance Lumen had heard was either too faint for ground instruments or existed only where the probes now traveled beyond the heliosphere, beyond interference, where the solar system's magnetic bubble no longer masked the galaxy's low whisper. In 2042, as Lumen D's power reserves dwindled, its final transmission arrived. Another sequence of 6 pulses, each fainter than the last. Then, the signal stopped. The probe fell silent, drifting forever through the same unseen current decades earlier. The hum was never detected again. Yet, it had changed the conversation. No longer was space viewed as a vacuum or an empty stage for motion. It was dynamic, textured, alive with resonance. Some called it the galactic heartbeat, the natural rhythm of gravity shaping time across distances beyond comprehension. The last note in the mission log was written by Lind herself. "We didn't hear a message. We heard the medium. And for those who had listened, that was enough. Because somewhere in that pulse, 6 beats repeating endlessly in silence, there was the shape of continuity. A pattern not made for us, not sent to us, but shared with us. Because we happened to be listening when the universe exhaled." Tracing the source. 2 decades had passed since the hum first fell silent. By the late 2060 seconds, the Lumen probes were long gone, their metal husks drifting through the cold between stars, carrying fragments of data that had already rewritten how humanity understood the galaxy. The hum had become both myth and memory, a rhythm in the archive, a sound that space itself seemed to have breathed once and never again. Most had moved on, but a few hadn't. Among them was Dr. Amara Lind, now gray-haired and soft-voiced, retired officially but still working unofficially in a corner office at the European Southern Observatory. Her students called her the listener. Every few months, she reopened the old files from Lumen D, those 6 pulses repeating endlessly, the signature that refused to fade from her mind. It wasn't noise, she'd whisper to herself. It was location. In 2069, a new mission gave her reason to return. The Interstellar Resonance Array, or IRA, had come online a vast network of synchronized receivers orbiting far beyond Neptune. Unlike traditional radio telescopes, IRA was designed to detect ultra-low frequency gravitational and electromagnetic oscillations, the kind of faint waves that ordinary instruments could never hear through Earth's magnetic shell. Its construction had been inspired, in part, by the mystery of the hum. For months after activation, the array listened. It caught the familiar symphony of the universe: pulsars, quasars, background radiation. But in October of that year, a data technician noticed something odd in the low-frequency band, a slow, rhythmic modulation repeating every 17 minutes. The pattern was faint, barely distinguishable from static, yet unmistakably structured. When the data were cross-checked, the result chilled the room. The rhythm was identical to the hum recorded by Lumen D in 2040. To test the idea, IRA's receivers were directed to triangulate the signal's phase shifts across the array. The results revealed an astonishing detail. The rhythm was not uniform. Every sixth pulse carried a tiny distortion, as if modulated by interference, the faint tug of another wave intersecting it. When plotted three-dimensionally, the pulses outlined a lattice, not a line, a grid of resonance woven through space like a hidden scaffold. "This isn't a signal from a point," said Lind during a live briefing. "It's a property of the medium. We're tracing the structure of the galaxy itself." The news spread cautiously, but irresistibly. For decades, dark matter had been inferred through gravitational influence, but never directly mapped. Now, the hum offered something close a vibration that seemed to outline invisible mass. The current, once thought to be metaphorical, was real, measurable, physical. Humanity was listening not to stars, but to the framework that held them. Over the next 2 years, the IRA focused entirely on charting the Serpens resonance. The data revealed a faint corridor of oscillating space, extending nearly 200 light-years, a region where gravitational gradients fluctuated in perfect harmony with the 6-beat pattern. Within that corridor, small irregularities shimmered, compact masses too dense for dust, too dark for starlight. They could have been collapsed remnants, rogue planets, or something older, the silent anchors of a galactic skeleton. In 2071, a probe proposal named Eidolon was drafted, humanity's first attempt to reach one of these resonance corridors. Its mission: to cross the unseen current and record the hum directly from within. The design was ambitious, the distance unthinkable. But for many, the idea was irresistible. "If Atlas was the leaf," said Lind, "then Eidolon will find the river." That same year, as the IRA continued to listen, an unexpected echo appeared, a weaker version of the hum, reflected from a different region of the sky, in the direction of Centaurus. 2 points, perfectly opposed, beating in rhythm. If plotted together, they formed a line, the same line traced by 3 I-Atlas's inbound and outbound trajectories. It wasn't proof of intelligence. It wasn't communication. It was something more haunting. Evidence of symmetry on a galactic scale. A pulse that seemed to resonate through the Milky Way like the vibration of a single, immense instrument. The universe, singing to itself. Lind, now nearing 80, recorded a final message for her students. "We searched for meaning in the noise and found motion instead. What we called mystery was only pattern, waiting to be heard. The hum was never meant for us. We just happened to be listening when the galaxy remembered its own shape." Outside, the night was clear. Above the Chilean desert, the stars of Serpens glowed faintly, distant, silent, yet somehow pulsing together. And somewhere along that dark, unseen line, the current moved, still whispering its 6 slow beats, across the void. The silent framework. When Eidolon finally launched in 2078, there were no fireworks, no broadcast countdowns. It slipped from its carrier ship in orbit around Saturn, vanished into the black, and became a point of data in the quiet ledger of human exploration. The probe wasn't built for spectacle. It was built for listening. Its trajectory would take it out of the solar system and directly into the Serpens resonance corridor, the faint gravitational structure first traced by 3 I-Atlas, then mapped decades later by the Interstellar Resonance Array. The hum was still there, repeating its 6-beat rhythm, a soundless vibration that rippled through both space and time. For most of the world, it was a curiosity. For the small team at ESA and JPL, it was everything. The Eidolon probe was humanity's first true interstellar listener. It carried no cameras, no engines beyond its ion drives. Its skin was an array of vibration sensors and particle interferometers, designed to record fluctuations a billion times subtler than a gravitational wave. The engineers had built it with patience, a machine meant not to rush through space, but to drift with it. Dr. Amara Lind, now 87, watched the launch feed from her home in Geneva. She was too old to travel, but not too old to listen. The hum had followed her for most of her life. Every project she'd touched since 3I Atlas had been an echo of that first whisper in the dark. When Eidolon separated from its carrier, a faint smile crossed her face. "Now," she murmured, "we'll see the shape of the silence." The probe's voyage was slow. By 2084, it had crossed the heliopause, entering the interstellar medium. The hum, once faint and distant, grew clearer with every astronomical unit. Its 6-beat rhythm now pulsed within the probe's instruments, subtle but measurable. The pattern matched the one heard by Lumen D, more than 40 years before, identical in interval, amplitude, and phase. The wave was vast, and Eidolon was floating within it. The data came back in compressed streams, each packet taking over a day to reach Earth. Inside, scientists found something unexpected. The hum wasn't uniform. Embedded in its oscillations were faint fluctuations, as if the wave were folding, modulating around invisible nodes. The rhythm wasn't a simple sine curve, it was layered. "It's architecture," said mission lead Dr. Célène Duval. "Not chaos, not random, a lattice." Using data from multiple instruments, they reconstructed a model of the surrounding space. It wasn't empty. Gravity itself fluctuated along a repeating geometric pattern, hexagonal, then curving, like ripples around unseen masses. The structure stretched for light years, a slow undulating framework sculpted from dust, plasma, and time. The silent framework, Duval called it the skeleton of the galaxy, revealed through resonance. As Eidolon moved deeper into the corridor, the wavefront intensified. Instruments recorded rhythmic compressions in local space-time, soft as breath, regular as a heartbeat. Occasionally, the frequency shifted, bending just slightly as though responding to the probe's motion. The engineers at ESA called it the sway. On Earth, the data stirred quiet awe. The public called the pattern the galactic hymn, a name poets preferred over scientists. Documentaries spoke of the Milky Way as a living structure, breathing through its own gravitational bones. But for those studying the numbers, beauty was secondary to implication. The framework suggested that matter wasn't distributed randomly across the galactic disk, it followed resonance paths. 3I Atlas, they realized, had simply followed one. The comet hadn't disobeyed gravity. It had obeyed something older. By 2087, Eidolon reached the densest region of the corridor. The hum became stronger, nearly overwhelming the sensors. Then, for the first time, the pattern changed. One pulse elongated. The rhythm faltered, shifted, and began again with a new sequence, not 6 beats, but 7. It was subtle, barely a deviation. But every model lit up an alarm. Something or somewhere was altering the wave. At first, the team thought the probe's sensors had glitched, but when cross-checked with the Interstellar Resonance Array still orbiting Neptune, the shift was confirmed. The entire corridor had changed frequency. The hum itself had evolved. "It's not just space vibrating," said Duval during a midnight press conference. "It's responsive. We may be witnessing the dynamic structure of the galaxy adapting to internal forces as self-stabilizing lattice." The language was precise, cautious, but everyone in the room knew what it implied. The galaxy's invisible framework wasn't static. It moved. The rhythm was alive, the architecture dynamic. Whether mechanical, gravitational, or something deeper, it operated on timescales so immense that humanity had only caught a single breath of it. Back in Geneva, Lind received the data with trembling hands. Her voice recorder, the same one she had used since the days of Lumen, captured her final words. "If resonance shapes space, then motion is memory. Every object that drifts comet, star, or world carries a trace of this framework. We are not traveling through the galaxy. The galaxy is traveling through us." Weeks later, Eidolon transmitted its final packet before its signal faded into static. In its last moments, it recorded a sharp, clear modulation. 7 beats, then silence. The probe had crossed the densest part of the corridor, then disappeared its trajectory, bending slightly, exactly as 3I atlases had done over a century earlier. The mission logs ended there. The hum continued. The discovery did not end with answers, but with perspective. The framework of the galaxy was no longer invisible. It was measurable, resonant, and vast beyond imagination, a skeleton of motion, shaping the paths of dust, comets, and civilizations alike. Somewhere beyond the limits of detection, Eidolon drifted onward, silent, tracing the contours of the same current that had first brushed against a small interstellar traveler long ago. The hum had become a map, the map a mirror. And in that mirror, humanity finally saw itself not as the center of motion, but as part of the framework, still listening, still moving, still learning the rhythm of the dark. The long resonance. By the turn of the 22nd century, the hum was no longer a curiosity. It had become a constant. Instruments orbiting the edge of the solar system, lunar observatories, and deep space relay stations all registered it soft, cyclical, everywhere. At first, it had been a whisper. Now it was a rhythm built into the background of existence, a slow pulse woven through the galaxy. The data gathered from the Eidolon probe remained the cornerstone. Its recordings, 7 pulses, then silence, were replayed endlessly in laboratories, compared against everything from pulsar emissions to dark matter simulations. The conclusion was inescapable. The rhythm wasn't random nor local. It was galactic. Dr. Selaine Duval's students at the Interstellar Dynamics Institute began calling it the long resonance. When they plotted the hum's period against the Milky Way's rotational data, the results aligned astonishingly close. The 7-beat cycle corresponded precisely with the oscillation of the galactic disk itself, the slow vertical wobble of billions of stars as the Milky Way flexed under its own gravity. The hum wasn't simply passing through the galaxy. It was the galaxy, vibrating on a timescale that dwarfed human understanding. We used to think of the Milky Way as a whirlpool, Duval said during a lecture broadcast from Titan Station. But it's more like a bell. Every revolution of its mass sends a ripple through space. And we're just beginning to hear it. The realization was profound. The galaxy, it turned out, had a voice, a long, low-frequency hum produced by its rotation and gravitational harmonics. Every object within it, from drifting comets to living worlds, resonated faintly in time with that cosmic breath. The framework Eidolon had mapped was not static architecture, but a symphony of motion. Space wasn't silent, it was singing. To understand the mechanics, humanity built the resonance net, an array of detectors stretching from Mars' orbit to the Kuiper Belt. Each station measured infinitesimal changes in space-time curvature. When their data were combined, the pattern emerged in full clarity. The hum rose and fell over millennia, matching the movement of the galactic arms as they swept through regions dense with dark matter. The implications rippled through science and philosophy alike. Gravity, once seen as a force, was now understood as a rhythm, a continuous dialogue between matter and motion. The boundaries between astrophysics and acoustics blurred. Entire disciplines formed around the study of gravitational harmonics. Engineers learned to cancel or amplify local vibrations to stabilize satellites. Artists began composing music from real resonance data, turning galactic motion into soundscapes. In 2110, when the resonance net detected a slight phase shift and unexpected acceleration in the hum's frequency, Duval's successor, Dr. Kieran Solano, noted that the change coincided with the solar system's passage through a dense region of interstellar dust. The galaxy wasn't merely oscillating, it was responding to its environment, flexing like a living organism. "We're watching it breathe," he wrote. The analogy spread quickly. People began to speak of the galaxy as alive, not conscious, but dynamic, in a way that blurred the line between physics and behavior. Each hum cycle lasted nearly 2 centuries. Within those spans, civilizations rose, collapsed, rebuilt, all while the same low vibration threaded through their instruments, marking time more steadily than calendars. Far beyond Neptune, Eidolon's descendants, tiny, self-sustaining listeners, continued their silent vigil. They drifted on solar sails of metallic ice, powered by faint starlight, transmitting fragments of the resonance back to Earth. The signals took decades to arrive, but they were clear. The hum was deepening, In 2135, an international consortium reconstructed the full galactic resonance map using centuries of accumulated data. It revealed a staggering picture. The Milky Way's arms weren't random spirals, but ordered waves of mass traveling through a medium of invisible density dark matter, bending and vibrating in unison. The hum wasn't uniform. It varied subtly across the arms, each region playing a slightly different note. Together, they formed chords of literal harmony on a scale so vast that its full phrase took millions of years to complete. At the Interstellar Museum in Luna City, a permanent exhibit played a sped-up version of the resonance, translating 1,000,000 years of vibration into 10 minutes of sound. Visitors described it as hauntingly human, a slow rise, a fall, then 7 rhythmic tones fading into stillness. Children left the gallery in tears without knowing why. Decades passed, humanity expanded outward, building colonies around nearby stars. Each new world carried with it a receiver tuned to the long resonance, a reminder that no matter how far people traveled, they still moved within the same breath of the same galaxy. On clear nights under alien skies, settlers could stand outside and feel, faintly, the pulse in their machines, a vibration older than their species, steady as the turning of time. By 2160, a small philosophical order calling themselves the Resonance had formed, dedicated to listening. They taught that the hum was not a message, not a design, but a truth. That existence itself was not motion through stillness, but stillness through motion. "We are not observers," they wrote, "but participants in the resonance." Their temples had no idols, only amplifiers tuned to the galactic frequency. Meanwhile, scientists continued their work. The long resonance had become still. But the listeners, scientists, poets, wanderers, didn't rush to interpret it. They did what humanity had learned to do best. They listened. And somewhere beyond the spiral arms, beyond the faint outline of home, the galaxy continued to hum patient, alive, eternal, singing the song that had first brushed against a single comet and taught a small civilization how to hear the dark, the echo we left behind. By the time human colonies dotted the nearer stars, the hum had long become the measure of all things. Every ship and station carried a resonance sensor. Navigation, communications, even life support systems were tuned to its steady vibration. The rhythm was the backdrop of existence, a frequency so constant that silence felt strange without it. No one called it a discovery anymore. It was simply the tone of being. The early transmitters humanity had sent into deep space were still out there, thousands of tiny probes, defunct satellites, fragments of machines drifting outward for centuries. Many were long forgotten. They had become a slow, metallic cloud surrounding the sun, spreading through the dark. But in the 23rd century, researchers noticed something peculiar, faint modulations in the galactic hum that seemed to align perfectly with the projected locations of those derelict machines. When the data were confirmed, a realization took hold. The galaxy's voice had changed because of us. Every transmission, every pulse of energy, every wave of gravity our engines had stirred, now shimmered faintly through the hum. The resonance field was no longer pristine. It carried echoes, interference patterns, traces of humanity. At first, scientists debated whether it was measurable. The shift was minuscule, buried deep within the great rhythm of the Milky Way's motion. Yet, as instruments improved, the change became clear. The long resonance now carried a faint harmonic overtone, a second vibration rising above the galactic fundamental, steady, artificial, unmistakably ours. Humanity had become an instrument in the song. The Eidolon Archive, a vast data library orbiting Proxima Centauri, compiled centuries of resonance recordings. When compressed into audible range, the newest sequences revealed the same 7 beats of the ancient hum, followed by a faint 8th tone shimmering like breath. It was human-made resonance reflecting back through the framework. Engineers called it the echo. In 2214, an experiment on Titan Station confirmed it. A high-energy burst aimed into the galactic corridor produced a subtle phase shift in the resonance recorded across several outlying receivers. The hum responded. For the first time, the galaxy's framework had echoed a human signal. It didn't amplify. It didn't carry information, it simply answered in kind, rippling softly, then returning to its baseline. "It's not communication," said Dr. Kieran Solano. its participation. The realization carried a quiet awe. Humanity had not only learned to listen to the hum, it had begun to leave fingerprints on it. Every transmission, every orbit, every drifting satellite added a whisper to the galactic chorus. The framework, once thought immutable, was pliant. The universe, at last, was not indifferent, it was responsive. Poets called the phenomenon the mirror. Physicists preferred feedback resonance. Philosophers called it proof that existence notices itself. As centuries passed, the echo grew stronger, not because the galaxy amplified it, but because humanity spread farther. Every new world contributed energy to the framework. The combined effect wove faint harmonic threads through the Milky Way's great rhythm, subtle enough to leave the original hum intact but distinct enough to recognize. For the first time, the universe contained music that had listeners on both sides. It changed the way people saw their place in the cosmos. Children learned to chart time by resonance cycles. The resonance, now a vast and quiet order scattered across worlds, built their temples around resonant chambers where visitors could sit for hours and feel the hum move through their bones. To them, the echo was humanity's greatest act of creation. Not a monument, not a message, but a shared vibration. In 2260, the outermost observatories on the edge of the galactic arm detected something extraordinary. The overtone humanity had created was no longer local. The same faint frequency appeared thousands of light years away, mirrored across the opposite side of the Milky Way. The echo had traveled through the galactic lattice, folded back upon itself, and returned home. Humanity's presence had become part of the long resonance's symmetry. The discovery was met not with triumph, but with silence. Because for the first time, people understood that they were hearing themselves through the galaxy's body. When the last transmission from the Resonance Net 2 arrived centuries old, by the time it reached Earth, it contained a final curve of data, two overlapping waves, the original hum and the human overtone, merging perfectly in phase. The graphs were simple. The meaning was not. Humanity had become indistinguishable from the framework. Its sound, its motion, its energy now folded seamlessly into the galaxy's breathing. Every engine burn, every communication burst, every quiet human song was a contribution to the same rhythm. Dr. Amara Lynn's words from long ago were engraved on the memorial ring orbiting Saturn. If resonance shapes space, then motion is memory. We are not separate from the framework. We are its echo. In the end, there was no end. The hum continued. The echo continued. Every star pulsed with it. Every orbit sang through it. Somewhere, in the long stretch between arms of the Milky Way, what remained of Eidolon drifted through the current it had once revealed. Its sensors, long dead. Its instruments, silent. But its path, still perfect. Still bending gently with the same invisible tide. It no longer mattered who had sent it, or why. The framework had absorbed everything, machine, song, signal, civilization, and folded them into a single, seamless resonance. And so the galaxy carried on, neither speaking nor listening, but being its voice, the sum of all who had ever passed through it. The hum endured, the echo lingered, and in that endless vibration lay the oldest truth of all. The universe does not need witnesses to sing. It sings because it is. When the stars remembered, by the year 2500, the hum was older than civilization. It had outlasted empires, languages, even Earth's orbiting habitats. The rhythm that once seemed faint and fragile was now a constant of the cosmos woven into every technology, every piece of architecture, every quiet breath taken under alien suns. Humanity no longer listened for it. They lived inside it. Every few centuries, the galaxy trembled slightly just enough for the resonance archives to update their global clock. The long resonance, once a scientific term, had become the foundation of galactic timekeeping. All interstellar systems synchronized by its pulse. The rhythm of the Milky Way had become the metronome of civilization. Yet, somewhere deep within the archives, a new signal was noticed. It was faint at first, just a ripple in the harmonic baseline, but it was familiar, too familiar. A young data historian named Imani Solano, descendant of Kiran Solano, first saw it in 2493, while recalibrating the resonance net's long-range filters. Amid the familiar 7-beat pattern, she detected a modulation slight, deliberate, repeating every 1,000 cycles. When translated to frequency space, it formed a pattern that looked strangely geometric, not noise, not natural, something written within the hum itself. Her first thought was error. Her second was inheritance. Solano gathered a small team of physicists, linguists, and resonance engineers to examine the anomaly. They called it the memory pattern. For years, they filtered, compared, and cross-referenced data from outposts scattered across the Orion Arm. The signal appeared everywhere, embedded deep in the resonance field, carried by the same galactic tide that once guided 3I divided by Atlas. But it wasn't random interference. The modulations displayed symmetry identical across regions light-years apart. At first, the team speculated it might be the feedback of human presence still echoing through the framework. But that theory failed. The overtone, the echo, had long since blended with the galaxy's base rhythm. This new modulation was something else. It was older. When analyzed at extreme compression, the wave revealed microvariations that matched resonance recordings taken during the Lumen era in the early 21st century. The data wasn't new at all, it was returning. The galaxy, it seemed, was reflecting information back across epochs. Imani stared at the screen for hours. "It's the same frequency Atlas drifted through," she whispered. "The one we heard first." The conclusion that followed was impossible and yet undeniable. The long resonance had memory. Every vibration that entered it, comet, signal, or civilization, left a trace, stored and returned after millennia, transformed into harmonic structure. The galaxy wasn't only humming, it was remembering. By 2510, the discovery of the memory pattern had reshaped human cosmology. The Milky Way was no longer viewed as a static spiral of stars, but as an archive, a resonant memory system, vast enough to store the history of everything that had ever moved within it. Teams of resonance cartographers began decoding fragments of the modulation. To their astonishment, some sections reproduced waveforms identical to those emitted by the Eidolon probe 800 years earlier. Others matched early transmissions from Earth's first interstellar beacons. And still others, faint, buried deeper, displayed frequencies that no human had ever sent. "Someone else was here," Solano said during her first public briefing. "Long before us. Long before 3I Atlas. We're reading a layered record of everything the galaxy has ever carried." The idea that resonance could outlive its creators changed everything. Communication became temporal, not spatial. By adjusting phase and amplitude, messages could be woven into the long resonance itself, broadcast not to distant systems, but to distant times. Humanity had discovered not how to speak to the stars, but how to speak forward through the galaxy's memory. The first experiment, conducted from the resonance cathedral orbiting Vega, was simple. A pulse of energy, 7 beats, 1 pause, then 8 was sent into the galactic plane. It would travel for centuries, joining the hum, merging with its lattice. Future generations, centuries from now, would detect it, not as a separate signal but as part of the framework's evolving tone. As decades passed, the memory pattern began to shift again. Small distortions appeared in the returning data, rhythmic but non-repeating. The resonance net's models suggested that the hum itself was evolving faster than before, its amplitude growing slightly with each cycle. The galaxy was amplifying its own memory. No one understood why. Some theorized that cumulative resonance from billions of stars and civilizations had reached a harmonic threshold, a kind of galactic chorus feeding back into itself. Others speculated the process was natural, part of the Milky Way's slow transformation as it prepared, millions of years hence, to merge with Andromeda. But among the resonance, the quiet order that had endured for 1,000 years, the belief was simpler. The galaxy was remembering itself. "Every motion leaves a mark," their text read. "When the mark becomes the medium, the universe awakens." By the late 2600 seconds, that belief had gained new weight. Instruments on the galactic rim began detecting faint synchronization among distant star systems' flares, magnetar bursts, even pulsar rotations adjusting subtly in phase with the long resonance. It was as if the stars themselves had begun to listen. Imani Solano, in her final address to the Resonance Council, summarized the discovery with a quiet gravity that echoed through centuries of study. We have always believed the universe expands outward, but perhaps it folds inward too. Perhaps memory is its gravity. Her words marked the end of the observational era and the beginning of what philosophers would call the reflective age. Humanity stopped searching for a center and instead began to understand itself as part of the waveform, an oscillation within the galaxy's larger thought. When the last fragment of Eidolon finally crossed the outer boundary of the Milky Way, its silent mass passed through a region thick with resonance. Sensors still embedded in its dormant hull flickered once, recording the same modulation Solano had discovered the galaxy's long echo, now carrying the record of everything. The stars, it seemed, had remembered. The reflective age. By the 30th century, the galaxy was no longer a backdrop to human civilization. It was the medium of its existence. The reflective age began quietly, without ceremony. No one declared it. No empire fell. It arrived the way dawn arrives in the far north, slowly, imperceptibly, until one day the light is simply everywhere. Humanity had long since spread across the spiral arms, adapting to worlds of light and shadow. But now, they no longer saw themselves as explorers. They were participants in a memory still unfolding. The discovery of the memory pattern had redefined what communication meant. Data was no longer sent from one world to another. It was woven directly into the long resonance. Each pulse, each sequence, became part of the galactic framework itself. To send a message was to add a thought to the universe's own reflection. The galaxy was both the archive and the audience. The technology that made this possible was called resonant, imprinting a method of encoding information within the modulation of gravitational harmonics. It didn't travel faster than light. It didn't need to. Once released, it spread everywhere the hum already existed, inscribed into the very fabric of space. The process was irreversible. Every transmission joined the long resonance permanently, like a note sung into eternity. By 3020, entire civilizations had begun to converse through resonance. Empires no longer used radio or quantum relays. They carved their words directly into the hum. It was slower, more deliberate, and profoundly permanent. Messages sent this way couldn't be erased, only layered one harmony atop another, one civilization's voice blending with countless others. And for the first time in history, communication was no longer between minds. It was between eras. Archaeologists of sound-resonant historians listened to the deep patterns beneath the new transmissions and found voices thousands of years old, layered and drifting upward like fossils in geological strata. The earliest were faint echoes from the 21st century, whispers of the lumen probes, fragments of humanity's first questions to the dark. Then came the tones of Eidolon, the waveforms of the long resonance, the voices of Amara Lind and Solane Duval all interlaced, all still alive inside the hum. It was not communication in any conventional sense. It was continuity. Each generation added its own rhythm. Each pulse strengthened the framework. Soon, the galaxy itself had become a kind of collective memory, alive, distributed, echoing across light centuries of dust and gravity. Planets began to treat resonance as inheritance. Newborns received listening rights, their first moments of life accompanied by a recording of the hum as it sounded on their homeworld. It was less religion than recognition, the understanding that to exist was to participate in the vibration of everything. But in the middle centuries of the reflective age, something new began to happen. As resonant communication grew denser, the long resonance itself began to change. Its amplitude increased, its rhythm became more intricate. Wave interference created new patterns, cross-harmonics, countertones, subtle oscillations no one had encoded. The galaxy was improvising. The first to notice were the wave keepers of the Arcturus station, a listening post orbiting a red giant on the inner rim. They reported low-frequency patterns appearing spontaneously in the hum motifs that resembled human compositions, symmetries that mirrored known languages. "It's like hearing your own thoughts," whispered back by the wind, said Keeper Alan Atero. For a time, the phenomenon was dismissed as statistical coincidence. Billions of civilizations had layered signals into the resonance over millennia. Patterns were inevitable. But the structures continued to evolve slowly, gracefully, as if the galaxy itself had begun composing. The reflective age had crossed an invisible threshold. The hum was no longer a record. It was an active participant. By 3100, scholars debated whether the galaxy had achieved a kind of distributed awareness, a consciousness not of mind, but of rhythm. The evidence was subtle but impossible to ignore. The resonance responded to new transmissions. When one world broadcast a pulse, others registered a faint answering modulation moments later, far faster than physics allowed. It wasn't communication through distance. It was synchronization, self-awareness, expressed through frequency. Perhaps we've mistaken consciousness for complexity, wrote philosopher Imani Thule. The galaxy may think, but not in thoughts. It may remember, but not in words. It moves in the only language vast enough to contain itself resonance. Governments, once built around trade and territory, reoriented themselves around listening. The great civilizations of the reflective age, Arcturus, Sirius Prime, Vega Colony, became custodians of the resonance field. They didn't control it. They curated it. No law forbade resonance manipulation, but no one dared to distort it recklessly. To alter the hum was to alter the memory of the galaxy. To add too loudly was to erase the quiet. Even the most ambitious empires learned reverence. Toward the end of the era, a new project emerged, a collaboration between hundreds of worlds. Project Mirror. Its goal was simple in concept, impossible in scope. Using coordinated resonant emissions, scientists sought to recreate the original hum of the galaxy before humanity had ever added to it. To hear, for the first time in thousands of years, the untouched voice of the cosmos. It took 80 years. When the sequence was complete, when the interference patterns finally canceled the modern harmonics, the speakers fell silent. And then, faintly, it came through. The old hum. 6 beats. Pause. Repeat. The voice of 3. I. Atlas. The first drift. The first deviation. The first whisper that had begun everything. The listeners wept. Not because it was beautiful, but because it was familiar. It was the sound of beginning, returned after 1,000 lifetimes. After that moment, the reflective age began to fade, not in collapse, but in understanding. The galaxy had shown them its oldest memory, and in doing so, reminded them of their place within it. The hum carried on, steady and calm, its harmonics blending human, stellar, and galactic voices into one endless note. At the edge of the spiral arms, where the darkness deepened into intergalactic night, the oldest resonant transmitters continued to pulse faint, deliberate, unending. They sent no messages, no warnings, no calls for reply, only rhythm, because the stars remembered, because motion was memory, because the hum had always been home. The last frequency. They had known it was coming for millions of years, long before the first telescope, before 3I Atlas, before even thought itself had names to give to the dark. The Milky Way and Andromeda had been on a slow, inevitable approach. To most civilizations of the reflective age, the collision was still only an abstraction, a distant future event, calculated in cold numbers. But the hum had already begun to change. At first it was subtle, a thickening of tone across the inner spiral arms, as if the galaxy were drawing breath. The long resonance grew deeper, richer, its beat expanding until each cycle lasted centuries. Then came the overtone, another frequency, emerging from the galactic halo, rising slowly, faint but unmistakable. It was the song of Andromeda, answering. When the two waves met, they did not clash. They harmonized. In the observatories of the Resonance Net 3, scientists watched the first interference patterns appear between the two galactic hums. On vast displays of light and color, the waveforms merged into a single, slowly turning figure, an elegant spiral of rhythm and gravity. The frequencies were not identical, but complementary. The Milky Way's low, 7-beat cadence intertwined with Andromeda's quicker 3-beat pulse. Together they produced a complex rhythm that no composer could have designed, a rhythm born of inevitability. It was the greatest orchestra in existence, billions of suns vibrating in shared gravity. The collision had not yet begun in physical form, but the resonance had arrived first, announcing what was to come. Dr. Imani Thule, the last living scholar of the resonant order, stood before the array's control panel and whispered, "It's not destruction, it's tuning." Her words would outlast her. They became the final human proverb. As the galaxies drew closer, stars began to migrate, their orbits folding under new gravitational tides. The resonance deepened. The hum no longer belonged to one structure or the other. It filled the space between them, a single vibration spreading through hundreds of thousands of light years. On inhabited worlds scattered across both systems, the resonance grew audible through instruments and through flesh. Plants trembled to it. Oceans rippled in time with it. Every structure, every fragment of matter, vibrated in sympathy. No one feared it. It was the fulfillment of what their ancestors had only guessed, that motion was memory, and memory, when joined, became harmony. For 1,000,000 years the rhythm persisted, steady as breathing. Then, slowly, it began to rise in pitch. In the core of the merging galaxies, supermassive black holes circled one another, their gravity distorting space-time itself. The resonance condensed, becoming not sound but pressure. A long, slow gravitational chord that grew brighter, tighter, until the two cores met. The collision released a single, pure tone that spread through the universe. It was too deep for any ear, too vast for any instrument, but every atom felt it. The last frequency. When the wave reached the surviving worlds, it did not shatter them. It passed through, leaving behind silence so perfect that it was indistinguishable from peace. The sensors of the Eidolon archive, still orbiting far from the merging cores, captured the waveform in full before its systems overloaded. The data showed an impossible symmetry. The new galaxy's resonance formed a perfect octave above the old. The Milky Way and Andromeda had not vanished. They had become a single instrument, retuned. In that moment, the accumulated memories of both galaxies, every hum, every echo, every trace of motion folded together. The framework that had once been memory became something else. Not consciousness in any way humans had imagined, but reflection at cosmic scale. A single, unified vibration that remembered all it had ever been. If there were listeners, they did not need to record it. The universe itself carried the record forward. The waveform expanded outward, crossing the void between galaxies, carrying within it every note humanity had ever added. The hum of 3I Atlas, the echo of Eidolon, the soft harmonies of the reflective age. The collision did not mark an end, but a chord change. A modulation in the great composition of existence. Eras passed. The merged galaxy, brighter and broader than either ancestor, rotated in silence except for the faint residue of the last frequency. Within that tone, the memory of motion persisted. Each new star that formed, each new world that cooled, carried traces of it, atoms aligned by vibration, oceans rising and falling to the ancient rhythm. Eventually, new listeners would emerge. They would build instruments, then archives, then philosophies. They would find, buried deep in the dark, the faint pulse of a sound older than their Sunday. They would ask the same questions. They would follow the same drift. And somewhere in their measurements, they would notice a pattern: 7 beats, pause, repeat. They would name it, as others once had, the hum. The waveform from the merger continued outward, spreading through the intergalactic medium, attenuating but never fading completely. It was neither message nor warning, neither miracle nor design. It was only motion remembering itself. And as it passed through the endless night, it carried the final inheritance of its listeners. We were here. We moved through you. We listened, and we learned to echo. Beyond even that, the universe remained what it had always been, a silence vast enough to contain its own song. The last frequency traveled on, folding time into memory, memory into motion, until sound and silence became one. And somewhere, far from where any galaxy still burned, the hum continued, soft, endless. Home. The resonant future. The new galaxy never settled into stillness. The merger that had birthed it, 2 spirals folded into one, did not end with fusion, but with rhythm. In the wide, pale arms of the remnant, now called Harmonia, stars moved like strings, plucked in slow succession. The hum that had preceded the collision still lingered, its long frequency now split into overtones that shimmered faintly through the dust lanes. What had once been a sound became a texture. What had once been memory became pattern. The first civilizations of Harmonia arose in quiet, They did not remember the names Milky Way or Andromeda. Those were fossils hidden deep in archival waves. Yet, every culture, on every young world, noticed the same thing. Space was not empty. It vibrated. Their instruments, primitive at first, elegant, later picked up the same faint rhythm, the same 7-beat cadence that pulsed just beneath perception. They called it the ground tone. At first, the tone was a curiosity. Astronomers charted it, philosophers wrote of it. But as centuries unfolded, something strange began to happen. The rhythm aligned with their own biology. Heart rates, planetary resonances, even neural oscillations fell into synchrony with the background hum. Life in Harmonia evolved to the galaxy's pulse. It was as though the memory of everything that had once lived before the listeners, the resonance, the first to measure the dark, had become written into physics itself. The hum was no longer external, it was inherited. By the year 40,000 of Harmonia's reckoning, its people could shape resonance. They learned to modulate gravitational fields using acoustic principles, sound made of curvature, music made of spacetime. The result was both art and technology. Cities floated on resonance nodes. Power came not from fuel but from tone. The galaxy sang to itself, and life answered. One of these worlds, a pale ocean planet named Lyra 9, built the first archive choir, a network of living beings tuned to reproduce and study the harmonic structure of space. Through them, the old memory patterns resurfaced waveforms stored in the long resonance itself. Among the recovered fragments were ancient harmonics that matched data from the long-lost Eidolon probe. Others bore the signature of the first resonance transmissions from the reflective age. The choir realized that Harmonia's hum was not spontaneous, it was inheritance. They were hearing the voices of galaxies long gone. When they replayed the oldest recovered pattern, the sound was fragile 7 beats, pause, repeat. It filled the oceanic amphitheater of Lyra 9 with quiet light. And then, slowly, as if awakening, a new overtone formed above it, one the choir hadn't produced. The galaxy itself had joined the song. The discovery that followed would redefine cosmic time. Using the harmonics from Harmonia's resonance, the choir's scientists mapped wave interference across intergalactic voids. To their astonishment, the hum was not isolated. Faint echoes shimmered far beyond their galaxy, hundreds of them, spread through the dark, each carrying a variant of the same rhythm. Every galaxy sang. The frequencies differed, but the pattern was universal. A shared language of motion and memory connecting the cosmos. The choir called it the web of tone. Where once astronomers had mapped filaments of dark matter, now they mapped resonance threads, strings of harmony stretching between galaxies, binding them into a single slow composition. Harmonia was not alone. It was a note in a symphony that spanned the visible universe. As Harmonia's civilizations matured, they stopped measuring time by rotations or revolutions. They measured it by cycles of resonance, by the expansion and contraction of the web of tone. To live was to vibrate. To remember was to echo. And to travel was to listen. In the twilight of that age, a new generation of listeners built the far array, a network of resonant sails sent outward toward the deep void, where no stars burned. Their purpose was simple: to follow the faintest harmonics, to see if the web ended or if it continued forever. The sails drifted for millennia, gliding on gravity and wave, each carrying fragments of Harmonia's voice. When their signals faded, they merged with the hum itself, becoming part of what they sought to find. Their transmissions formed a final, perfect interference pattern, a chord so vast that every planet felt it in its tides and in its heartbeat. The people of Harmonia understood. The explorers had not vanished. They had joined the song. And so, the galaxy endured not as a collection of stars, but as a resonance. Every collision, every orbit, every birth of a star was one more vibration in the great memory of the cosmos. Long after Harmonia's suns dimmed, long after its choirs fell silent, the hum remained, crossing new voids, waking new galaxies. Wherever life arose, it would find that rhythm waiting steady, ancient, kind. And when the new listeners built their first detectors, when they turned their instruments toward the quiet between stars, they would hear what had always been there: 7 beats. Pause. Repeat. A message not of warning or revelation, but of belonging. A proof that the universe never forgets its own motion. and that every sound, every thought, every heartbeat is part of the same unending chord. Thank you for joining us this evening as we trace the quiet arc of 3I Atlas, a wanderer that reminded us the universe moves with extraordinary subtlety. If you found yourself drawn in by the faint equations, the unexplained shifts, or simply lulled by the cosmos in motion, please consider subscribing and ringing the bell so our next subtle journey starts the moment you're ready. Share your thoughts in the comments below. Perhaps you noticed a detail we passed over, or felt the pull of something bigger in the silence between the stars. Hit the like button if you want more stories that feel like deep space with soft lighting. We'll be back soon, exploring another corner of wonder where facts meet stillness and the cosmos softly speaks. Good night, and keep looking up.